Hello, my name is Logan Valdez, and this is my fifth lab report for Physics 2211. This presentation covers 6 sections: Introduction, Principles, Experiment/Tracker, Computational Model/Code, Results/Discussion, and Conclusion. This lab investigates the falling slinky. Using Tracker, we recorded the Y position of the bottom of a falling slinky over time. We then built a glow script model to predict the same motion. The key result: both data sets show the bottom stays stationary at first, but deviations appear once it begins to fall. The core principle is Newton's second law. F net equals m times a. From this we get the velocity and position update formulas used in our model. 3 forces are involved: gravity acting downward as negative mg, the slinky tension force acting upward as positive mg, and the drag force equal to negative bv squared times v hat, which always opposes motion. We drop the slinky from rest and track the bottom coil frame by frame in Tracker. Initial position was 0.0312, 0.508, 0 meters with 0 initial velocity. We calibrated the video using a reference height of 1.77 meters and used a slinky mass of 0.172 kilograms. Time step between data points was 0.0667 seconds. Computational model in GlowScript. I matched those same initial conditions: mass of 0.172 kilograms, initial position from Tracker, and 0 initial velocity. Gravity was set to 9.8 and the drag coefficient B was set to 7.9, determined through trial and error to best match our observed data. Loop 1. The first loop runs from t equals 0 to 3.73 seconds. Before the bottom starts moving, here gravity and tension cancel out to 0 net force, so the bottom stays stationary. The loop steps through time using the velocity and position update formulas. Loop 2. The second loop runs from 3.73 to 6.13 seconds. When the slinky is falling, the tension force is gone, so only gravity and drag act on the system. Net force is recalculated in each step and is used to update velocity and position. GlowScript output. This is the GlowScript simulation. The blue ball is the bottom of the slinky, and the green arrow is the upward tension force in phase 1, and the cyan arrow is the net downward force in phase 2. The simulation visually confirms the expected behavior. Observed versus expected. This graph overlays both data sets. Both lines hold flat near 0.5 meters during the stationary phase, then drop after about 3.7 seconds. The expected data falls faster than observed, meaning our model captures the general trend but has deviations which brings us to error. Sources of error. 3 main sources. First, manually tracking the slinky in Tracker is imprecise due to motion blur and video quality. Second, the drag coefficient was estimated by trial and error, not measured directly. Third, real-world external forces like slight swinging are not accounted for in the model. Conclusion. Takeaway. 2 questions. 2 takeaway questions. Why does the bottom stay stationary? Because the tension force equals gravity, so net force is 0 and the bottom doesn't move. When does it fall? Once the slinky fully collapses and tension disappears, gravity acts unopposed and the bottom falls. Thanks for watching and have a great day.